All right, everybody, welcome to the Spacecraft Seminar Series. This is Model-Based Systems Engineering for Spacecraft Development. This is a natural follow-on from the Introduction to MBSE. And if you haven't seen the Introduction to Systems Engineering or Intro to MBSE, those would be good starting points going into this. But we have a phenomenal guest here today, Thomas Gasque, who is a systems engineering professional with Delligatti Associates, and he'll give introduction all to his own. But thank you very much here for being here, Thomas, and please take it away.
Great, thank you, Michael. So, like Michael said, this is model-based systems engineering for spacecraft development. I'm really happy to put this together and present. This is something I really love, MBSE. So we're going to go through a quick introduction, just a little bit about me, the purpose of this presentation, an MBSE overview. We're going to talk the three pillars of MBSE, a little bit on the background for our example problem. And then the meat of this is applying the MBSE methodology. So we're going to walk through all of these steps that you see over here on the right. This is a simplified MBSE methodology. And then at the end, we're going to summarize everything and cover questions. And if you have any questions throughout this, you don't have to wait till the end. Just feel free to jump in at any time. I want this to be kind of more of a conversation. So please just feel comfortable jumping in, interrupting me, any questions you have. And then I have several things cited, different papers throughout this presentation. I have my references at the end. So I am Thomas Gasque. A little bit about my background as far as academics and certifications. I went to the University of Alabama in Huntsville. I'm actually still a student there, believe it or not. So I started back in the day as a mechanical engineer. I got my Bachelor of Science in Mechanical Engineering with concentration in aerospace. Then I went back years later and got my master's in systems engineering. And that's where I really discovered MBSE and kind of fell in love with this discipline. And right now I'm pursuing a PhD in systems engineering under Dr. Dale Thomas. There's several certifications out there. I'm not sure if you guys are tracking the object management group. There's the OCSMP, which is the Certified Systems Modeling Professional. There's 4 levels of those, the highest one being the advanced. So I got that one maybe a year and a half ago. I went through all of those, and then I'm working my way through the UML certifications as well. So I'm an intermediate for the UML certification from OMG. There's one more after that I'm kind of studying for. I think it's going to be pretty tough. But background, I work for Intuitive Research and Technology Corporation, which is a company here in Huntsville, where I'm out of. And I worked there for several years. I was a mechanical engineer for a few years and switched over to systems engineering. And I led a lot of projects, a lot of MBSE related projects for DoD customers here on Redstone Arsenal. Now I work for Delligatti Associates, which we do is primarily MBSE training and consulting. There's 2 divisions of the company. So I'm the Director of Consulting Services. That's kind of my domain. So I come in and help people with project-specific MBSE needs. And then the other side of the company is training. So we have 2 training courses. And I help out quite a bit there as far as teaching our MBSE Accelerator training course. So a lot of this that I'm going to talk about, I'm really comfortable with because I teach these courses and it hits a lot of the same topics. And then I put some contact info here. This is my UAH email address. If you guys have any questions or think of anything after this, I'm always happy to talk MBSE methodology and answer any questions you have. So just feel free to reach out. So the purpose of this, kind of like we talked about, is to discuss how to implement an MBSE approach for developing spacecraft. And the reference material that I'm using is this book by Friedenthal, Sanford Friedenthal. It's Architecting Spacecraft with SysML. It's a really good reference to have. I mean, it's pretty spot on for what the purpose of this presentation is. And there's even an example model that you can download. So a lot of the diagrams we're going to see in the artifacts we're going to talk about a model, you can go download that model and play around with it yourself if you have access to Cameo or Magic Draw. But as we walk through the MBSE methodology that he lays out, we're going to review the artifacts from that and try to discuss the benefits, like how does this help us over doing the traditional document-based systems engineering approach. That's what we really want to focus on, because there's a lot of benefits to adopting MBSE. So before we dive into that, I just want to cover a little bit about what MBSE is. I have the ACSI definition here. I'm not going to read it to you guys and put you to sleep. But the big thing here, you can see on the right, is we're trying to move away from document-centric systems engineering to model-centric. So we want the model to be the primary artifact of the systems engineering process. We don't want to manage a bunch of documents, right? We want the model to serve as the source of truth for the system architecture and these systems engineering artifacts. So part of MBSE, the big thing is the language. So there's different languages we'll talk about, but the most prevalent one that I've seen as far as, training and doing consulting and actually being a practitioner is SysML, Systems Modeling Language. So that's what we're going to focus on for this presentation, but there are other alternatives out there that we'll talk through briefly. There's several values, of adopting MBSE over the document-based systems engineering approach. And I've cited a few references or a few papers here. We can manage increasing system complexity, improve design decisions, establish traceability in the model. There's a paper that talks about reducing development costs by doing MBSE. So these are sources from the literature that I've found. And then these last two is something that I've seen over the years and something we talk about at the company I work for, Delligatti Associates. It's the automated consistency among work products when a change occurs. So if the model is the source of truth and you change the name of your system, anywhere you use that block, it's going to get updated. You don't have to go into all these different documents and update the name of your system or, some text. That's the beautiful thing about the model, that these changes propagate through the model and you don't have to go track down all these things. You have a source of truth that you can work with. And then the rapid, definitive answers to stakeholders' questions. So if a stakeholder asks you, well, why does this requirement, exist? Why is this here? If you're in the model, you can easily go into the specification and look at the traceability and see what that trace is up to. Maybe it's a mission requirement or a stakeholder need. You can leverage the model to answer those questions on the fly instead of digging through, piles of documents or whatever it may be. So these are the two big things that we talk about with the company I work for. And then down here, this is important too, because in the ACSI systems engineering vision, it states that the future of systems engineering is predominantly model-based. So I put that here just to show that MBSE, at least from what I've seen, what I've read, just my experience, it's not going away anytime soon. This isn't a problem or something that we're going to talk about and then in a year it's gone, it's obsolete, right? This, from everything I've seen, it's here to stay. I'm sure it's going to evolve and things will change, but it seems like the future, like this says, is going to be really based on models instead of documents. So from here, we move into the three pillars of MBSE, and this is defined by Lenny Delligatti. So he wrote the book SysML Distilled, and that's where the three pillars of MBSE, as far as I can find in the literature, originated. And he talks about modeling language, modeling tool, and modeling methodology. So these are the three pillars. And we talked about SysML being the most prevalent of those, but there are others like unified modeling language that is used quite a bit for software systems. There's the Unified Architecture Framework modeling language. So if you're familiar with the DODAF type views, UPDM has evolved into UAF, and now the latest spec, UAF basically has its own modeling language that extends SysML, much like SysML extends UML. So these are very much related. But then there's other modeling tools out there in other languages. So there's the Arcadia Capella meta model that you could use, and then systems definition language. There's alternatives to these depending on what tool you use and maybe what is the best fit for your project. And then down here, similarly, there's different tools you can use. A lot of people are familiar with Cameo Systems Modeler or CATIA Magic. This is called many different things. And I think, Michael, we talked about this. Some people call it Magic Draw. They went through a rebranding process, I think, at some point this year or last year, where some of these things have changed. So we call it Cameo Systems Modeler, but there's many other alternative names, right, for kind of the same software.
It got purchased by Dassault Systems, and now Dassault has marketed a variety of different ways. They have cyber engineering suite is one that they offer that's kind of a slim down. They have Magic System of Systems Architect, which we refer to as Mimosa, but they've kind of packaged it differently. It's all generally the same stuff. It's just how many bells and whistles are you getting with the package?
Yes, exactly. That's the big difference, is the plugins that come with it. You know, some of these will have the UAF plugin where you have access to these type of things in the UAF modeling language. Others are a little more limited. So that's exactly right. But even aside from the Cameo, there's other tools out there that you can use. And then there's dependencies here. So say Vitek Genesis, that's a tool that I've seen that's really good, but they don't use SysML like Cameo does. They use the systems definition language, which is a little different. And you can generate some of the same SysML views, but the meta model for that tool is different. And same thing with Eclipse Capella. It kind of has its own meta model. So just be aware that, you know, when you're choosing a tool or a language and a methodology, there's some dependencies here. So if you pick a certain tool, you might not be working with SysML. So that's just important to keep in mind. And we'll talk through that a little more as we work through the methodology. And same thing over here, modeling methodology. There's a lot to choose from. Some of these are tightly coupled with, you know, tools and languages like Magic Grid. That's used quite a bit with Cameo Systems Modeler. Like if you have the Magic Grid Book of Knowledge, then all of their examples, they say it's independent, you could use any tool, but all of their examples, you know, it's all in Cameo or Magic Draw, right? So several options here to choose from as far as your three pillars. So what we're going to talk about today, we're going to scope it down. We're going to talk SysML. Like I said, that's the most prevalent. That's what I'm used to. That's what I've used the most. We're going to use Cameo or Magic Draw. That's what, if you go download the model, I think it says it's a Magic Draw. It was made in, I think, 18.5, version 18.5 of Magic Draw. But you should be able to open it with any of these versions of Cameo. And then the methodology, it's not the vanilla OSM, the Object-Oriented Systems Engineering method, but it's a tailored version of that methodology that for the reference material, the Architecting Spacecraft with SysML, Friedenthal basically took OSM and changed it up just a little bit to make it a little more simple and easier to follow. And that's what we're going to walk through today. Okay, so before we jump into the background, are there any questions?
For reference for everyone, how was the tailored object-oriented systems engineering method decided upon for the version that we're using here?
So that's what Friedenthal uses in this book, The Architecting Spacecraft with SysML. And I don't think he explicitly says it's OSM that's been tailored, but I'll show you a picture, I think a few slides later, that it's pretty clear. Like they're very similar. He just added a few things up front and then added an integration and verification piece at the end. But for the most part, you can look at them and see, yeah, these are similar. He just kind of changed OSM up. So that's what he uses in the book. So that's what I'm walking through today.
Awesome. Thank you.
Yep. So the background, before we just jump into the methodology, the system of interest in this book, the spacecraft itself, is a satellite, which he refers to as the FireSat. So I'm not sure if the group is familiar with that, but I pulled up a paper that had the original FireSat mission goals, as well as this OV1. So if you're familiar with like the DODAF views, this is a high level view of kind of the systems and how it interacts with different things. But this is the original FireSat ConOps diagram that I found in this paper, which I've referenced. But our system of interest is this satellite that we want to detect wildfires with. So I won't read through all the goals, but just to get an idea of the system we're working with, that we're going to develop, and the concept of operations, how it's going to be used. This kind of provides that background info. So timely detection of wildfires, reduce economic impact, collect data. So there's a lot of things in here that's really driving this process. So now we get into the meat of this presentation, which is applying this methodology. So this is that simplified methodology that I've shown. And the way we're going to do this is, if you've seen the intro to MBSE, then you're probably familiar with activity diagrams, but basically going to start at the top. This is the initial node and follow the arrows. So we're going to walk through this step by step. And once you get down here, this is just saying, this fork node is just saying that these paths happen concurrently. And then at the end, there's going to be this integrate and verify system. So we're going to walk through this in order. And even though we're kind of showing this as, first you plan the modeling effort, then you set up the model, a lot of this is iterative. So say even once you get down here to integrate and verify system, and you're in that part of the methodology, you could go back and update system requirements. You'll loop back or even change the setup of the model. You might have to change the organization to make room for test cases, so just keep that process as iterative, even though it's kind of shown as a straightforward top to bottom process. You're always going to loop back and update things as you better understand the system. So that first step, plan the modeling effort. The first thing, modeling objectives and scope. So the purpose of the model, that is so important. And you'd be surprised talking to teams that are doing MBSE, and you ask them this question: what is the purpose of the model? How is it helping you? And they don't have a good answer. They say, well, the customer wanted a model. We were told to do MBSE, so we're doing MBSE. But if you don't understand how it's going to benefit the customer or what you're getting out of the model, then you're going to waste a lot of time and energy. So that helps, if you understand the purpose, what you're trying to accomplish with the model, you can define the breadth, depth, and fidelity to support that purpose. So say, some projects I've worked, the primary output of the model, we really wanted to generate a system specification. That's kind of an easy first step to implement MBSE, define requirements, and generate a system spec from the model. So if you don't keep that in mind and you just keep working your way down, and all of a sudden you're writing requirements for this low-level component, you're wasting your time if that's not going to do anything. The customer doesn't need requirements at that level, right? So I can't stress that enough, to keep in mind the purpose of the model and let that drive the artifacts that you generate in the model. So another step here is pre-populate the model. A lot of organizations will have custom profiles or model libraries that they can use. We kind of had a standard custom profile. So say if you're doing OSM, there's the concept of a logical architecture versus a physical architecture. So you can have stereotypes associated with those two things to distinguish between the two different types of architecture. And that's not something that you have to just create from scratch every time. That could be in a custom profile that you just load if you know you're going to be using OSM. So things like that can kind of get you up and going quickly. Importing legacy artifacts. So say there was a satellite before the FireSat and you already have a list of requirements associated with that. You could pull that in to kind of get a head start too on what you're trying to do for your new system. That's very common to pull in kind of old artifacts, reuse what you can, update it to reflect the new needs of the system. Then you're not just starting with a blank sheet of paper. Another piece here is develop a schedule. So Friedenthal, in his example, he showed the milestones of the project going across the top here. So contract award, SRR, PDR, and then different artifacts that are going to be generated from the model. And he kind of associated each of the artifacts with the milestones and what maturity level they would be at by these milestones. So you don't necessarily have to do that in the model. Most of the projects I did, I think I had Microsoft Project. So I created like a Gantt chart outside of the model and had a schedule and everything laid out. But the approach he took, he's just showing that you could kind of tie these things together and have it directly in the model if you wanted. But that's not, you don't have to do it that way. Establish MBSE methodology and tool environment. So we talked about the 3 pillars. That's a big thing up front. And maybe organizations already have kind of a standard tool suite that they'd like to use. Maybe you don't have to make that decision. Maybe it's made for you or the customer wants it in a certain format. There's that possibility where some of these questions are already answered for you. But if you're just getting started with MBSE, then you need to select and figure out which of those options make the most sense for you. And then establish the MBSE training approach. I was happy to see this in the book because that's what, one of the primary things that we do at Delligatti Associates is train people on basically those 3 pillars. We have a class on just the language, SysML, and then another class that takes what you learn about the language and you apply it using a tool and a methodology. So that's big, especially if people aren't familiar, they're kind of a traditional systems engineer. It's hard to go do MBSE effectively if you're not really confident in SysML, you haven't used the tool, you have, no idea of what methodology to use. So training is an important piece here. And then here, another part of planning the modeling effort is tailoring a methodology. So you have to select one, like in this case, I'm showing OSM, which is from, if you have the book, A Practical Guide to SysML by Friedenthal, his other book, this is from that, which I've cited here. But you can see the similarities from OSM to the simplified methodology that he walks through in the Architecting Spacecraft book. A lot of similar things up front. He added the plan to modeling effort, which I think is a good addition. Whereas in OSM, you just jump into setting up the model. It doesn't mean you don't plan. It just wasn't part of the methodology itself. But over here, it's more explicitly called out. And then one thing that I like, he added this integration and verify system step at the end. So that's working your way up the right side of the V. If you think of the traditional systems engineering V, that right side is where you're doing the verification of components up to the system level, which isn't part of the vanilla OSM over here. So I'll pause for a second and just see if there's any questions. And you guys, again, just feel free to jump in at any time.
Ben, do you have any thoughts on what the purpose of our current model might be?
Sorry, what was that?
I was saying, do you have an idea of what the purpose of our current model might be? Because we're stepping through this, but Thomas has made clear that you have to understand what we're modeling for.
Mm-hmm. Let's see.
Put you on the spot, Ben.
What was that?
So he put you on the spot, Ben.
Yeah, a bit. Yeah, today's been a long day. Sorry, I do not have the mental capacity right now.
It's all good. I didn't know how much sleep you've gotten lately. I know it's been rough. I'd probably say that one, we need to communicate our system architecture to some of our individual subsystem teams. We need to be able to relate our requirements to some of those system architecture and design components, which I think Tom's going to get into shortly. But a lot of it is about internal stakeholder communication at the moment, and then eventually we're going to be getting into model-based reviews for external stakeholder communication. So I'd say that's probably some of our main purposes.
Nice. Yeah, as long as you have a good idea of what that is, then you can kind of focus your efforts on meeting those needs, right? So if you don't really have that in mind, I don't know, maybe you see this perform analysis and you're like, oh, cool, let's go build some parametric diagrams because that's fun and that's interesting, but maybe not going to serve a purpose or meet those needs, right? If you're just trying to communicate the architecture effectively and have that flow down to drive kind of the design of subsystems or components. Yeah, so that's all I'm trying to reiterate, is that keep the purpose in mind. So that'll keep you from going down these rabbit holes that aren't going to help you achieve anything. So the next step, set up the model. So now we're actually getting into the model itself. And I'm just going to show this here, how set up the model decomposes into these other two, but you can kind of think of any of these steps, say analyze mission and stakeholder needs. There's probably going to be multiple steps involved with this one action, right? And it could kind of decompose into something similar here. I'm just showing it for setup model because the two major steps here is establish modeling standards and conventions, and then organize the model. So organizing the model, it's really nice if an organization has a pre-built model template. We had that at so we have that kind of for when we do consulting with the company I'm with now, but at some of my previous work, there was model templates available that basically made the projects consistent. So say you're working 3-4 different MBSE efforts. If you're all using or working on a similar model template and the models are organized the same, it's really easy to navigate, right? You don't have to think, well, I'm doing project A and it's organized completely different than project B. It's just nice. It'll save you time, and it's really easy to go from project to project if it's organized the same. But if that doesn't exist, you absolutely can create a model structure from scratch. And really it's up to you to how to best organize that. And it might take some time to figure out what works and what doesn't, but this is what Friedenthal has laid out here, and you can visualize it. I liked just looking in the containment tree to see how things are structured, but you can have package diagrams to show how your model is organized and the package structures. And then one thing we had talked about, Michael, was the different standards or specifications that you could conform to. So I think you had mentioned MIL standard 490 is a good one. One thing that we had used in the past is this data item description, this 81431A. It's this defines a way to structure a system and subsystem specification. So think up here in requirements. This would apply for your requirements. It's going to structure the requirements of your system in a way that's consistent with the standard. So anything like that to kind of improve consistency or to conform to something instead of just making it up is probably going to be beneficial. The other part of this is establishing the modeling standards and conventions. So there's a lot of things you can and can't do just based on language law with SysML, right? So the SysML specification explicitly calls out things that are illegal or that you shouldn't do, but there's some things that kind of fall into a gray area. It's not necessarily wrong, but it's better to be consistent, falls under the category of more style. So like one thing is naming conventions. You know, a lot of people use lowercase names for elements of usage and then uppercase for elements of definition. That's not part of the language. It's just kind of good practice, and then it's easy to recognize those things in the model. Other things like diagram types. I mean, there's good reason to use activity versus sequence diagram, but maybe if something kind of falls in the middle, you lean one way versus the other. It's like, well, if we could do it with either one, let's go one or the other, right? This is a good one. All blocks must have a description in the specification field. And I think that should actually be documentation field. So think of if you define the blocks in your model, you might know very well what that is, what that represents. But if someone just read the name of it, they might not have a good idea of what that block is there for. So maybe you don't have to have a description for every single element, but blocks, you know, that's a good thing to have elaborate on a little bit in documentation. Maybe packages, so you know what the purpose of certain packages are in your model organization. Then there's other things that, again, it's just not covered by language law that you could define as a modeling standard or convention. And something really cool about using the model is some of these can be enforced using validation suites. So I'm not sure if anyone has created validation rules or validation suites, but they can automatically check your model for some of these things. So like where we have this one, a block may not be owned or may not own other blocks. Some people get the idea of the composition association and containment confused. They think if a block owns another block, that means there's a part-whole relationship. But that's different than having a composite association show that one block is a part property, is typing a part property of another block. So sometimes it's better to just say, we're not going to do this at all because people will get confused on what that means. And in that case, you can create validation rules that will check for that. So if somebody does it, there'll be an error that comes up in the model and you can go fix it. So it's not like you have to manually check for all of these. Some of these you can automate. But some conventions may require manual checking. So like a use case, if someone doesn't use a verb noun, it's gonna be hard to write a validation rule to check that. You know, maybe someday with, there'd be a way to do it. But right now, I don't think there's a good way to check for something like that. That just requires a human to understand that the naming is wrong there. So now we're moving down to analyze mission and stakeholder needs. And again, now that we've moved past this fork, really this maintain requirements traceability, this one that we're about to talk about, and perform analysis, these can all happen concurrently. So I'm just going to pause for a second, see if there's any questions.
Good here at the moment.
Okay. So one of the first things that you'll do once you have the model set up and organized is start identifying stakeholders and their concerns. And you actually represent these in the model as elements. So you're going to model each stakeholder and viewpoint. So the viewpoint is going to encompass the stakeholder and what their concerns are. And then the views conform to that. And you usually have tables or diagrams or something to kind of show how to represent that view from the stakeholder, right? So the way we teach it at Delligatti Associates is the stakeholder concerns is one of the primary things that guide the model purpose, right? So people ask us, how do you know when the model is complete or if you've modeled enough? And if you're capturing stakeholder concerns in the model and then generating artifacts in the model to satisfy those concerns, then once you have everything addressed and there's a satisfied relationship between artifacts and each one of these concerns, then you know you've addressed everything, right? So let that kind of drive the purpose. So say you have this sponsor that's concerned about satisfying the mission requirements within cost and schedule. You could have parametric diagrams that are estimating cost of the system that's going to satisfy this concern. You're going to show that, well, with this cost roll up, we're within the budget or we're not, right? So that's a big part of traceability too. A lot of people with traceability, you think requirements, deriving system requirements from the high level mission requirements, but you can establish these dependencies and traceability from even concerns to model artifacts like this. So from here, we can start defining the mission context. And this is where the model really starts to take shape, right? We've talked about organization, talked about stakeholders and their concerns, what they're worried about. Well, now we're actually defining structural elements here on a BDD. And with the mission context here, we're basically defining all the elements that the system of interest will interact with. So this isn't going to include things like the GPS, fire department, the Earth, space environment, all of these things that are going to provide some type of interaction with our system. And then down below, there's a mission enterprise. So the way this is organized is there's the high-level mission context with all these things, and then the mission enterprise is what the spacecraft directly interfaces with. So the ground station, the launch vehicle, these type things. So you don't really have to break it up between mission context and mission enterprise. I've seen a lot of high-level context blocks just have everything underneath it. But I do like how this mission enterprise breaks it up a little bit to where these things directly interfacing are what Friedenthal calls the primary mission elements are within here. So now we have our system of interest here, the spacecraft itself defined as a block. So we had modeled the stakeholders before. Now we can start looking at mission objectives. And these can be represented as use cases. So if you go back and look at some of the concerns or the high-level goals that we talked about in the background, this is going to be very much related. So this is just a way to visualize the high-level goals of the system and then what stakeholders are associated with those. So you can think of this as the Forest Service wants to use the system to detect and monitor forest fires in US and Canada, right? And then down here, the operator wants to provide forest fire data in near real time. So we start defining the high level goals of the system and then making the relationships to each of the stakeholders that we define too. And this is going to help drive the purpose of your model too. So this is really going to drive the behavior that you need out of the system to achieve these goals. So this piece, define mission requirements. So some projects that I worked, we didn't really have to, I guess, elicit this from stakeholders. And this is, again, where tailoring maybe comes in handy, or to keep the purpose in mind. Like, we had some documents that were just handed to us, and they said, here's the high-level mission requirements, here's the things we need the system to do, and then you can use those to derive system-level requirements. But if you don't have that luxury, maybe you have to elicit these from the stakeholders and get the high-level kind of source mission requirements. And a lot of times this isn't going to be in your typical shall statement form. When people think requirements or system requirement, it's usually the system shall whatever. So this, the way, at least in the example, it's more just kind of information. So resolution, 50-meter resolution, coverage, specified forest areas within the US at least twice daily. So these are going to be kind of squishy, but they're the high-level source mission requirements that you're going to use to derive more refined requirements and your system-level requirements. So here we start defining the mission behavior. So you can think of each of these as mission functions. And this isn't just behavior of the system. This will involve the system interacting with those other elements from the mission context, if you remember the BDD. So the launch vehicle is probably responsible for launching the spacecraft. But you can think of this as high-level mission functions, and each one of these, it will most likely decompose further, so you can see the behavior involved with each of these functions. So now you can start thinking, what to perform a mission, what needs to happen, what behavior needs to happen to actually execute a mission. And then you don't have to have all the detail here, just start at a high level, and then you can dive down into each one of these. So I think the example we're going to look at is maintain spacecraft operations. So when you see this rake symbol here, that means there's an activity basically set as the behavior for this action or some other behavior, right? So you can dive into this and see the details, which is here. So that one action we were looking at, if you dive into it, this is what's involved. And then that just allows to elaborate a little further on the behavior needed. And in this diagram specifically, they've started to allocate behavior to the mission or structural elements. So you can use swim lanes to start saying, well, the spacecraft is responsible for receiving a ground command, but the ground station is the one responsible for sending the command, right? And for monitoring telemetry. So you can do this as you start decomposing different behaviors of the system. You can start allocating that to even subsystems or lower level components, right? We're still talking at the high level mission behavior. So we're looking at system level and then pieces within that mission enterprise. But you can carry it down further and start allocating to even subsystems and components. Then right now, this is pretty simple. We're using control flow, and there's nothing typing the pins here for the actions. But eventually you'll see as this gets refined, maybe there's things flowing, object flows from one action to another. So there would be a command going from here to here. Whereas right now it's just shown as a blank object flow. So you'll add more detail as you better understand the system. And then you can start adding that to your model. So over here, you can kind of see these two pins are typed, even though they're not connected to anything. Provide electrical power. The launch vehicle power is what's coming into that pin. That's the type of object. So now we're talking about specifying system requirements. And this is interesting to me because, instead of just jumping right into writing text-based requirements, in the reference material, they walk through creating some of these views of the system first, right? Which is how a lot of the projects I've worked has always approached it. You don't just jump into writing the system shall do this or that or have this interface. It's better to use the model to kind of flesh out those details and then use that to drive what the textual requirements should be. So instead of jumping straight to that, we start defining what the spacecraft external interfaces are. And this is shown on an IVD. So if you remember that mission context block, now we're showing all of those blocks as part properties of the mission context. So you can start seeing what connects to what and what interface is there. So what entities are connected, how are they connected, what's flowing across the interface. So you can see some item flows here. Could be material or energy or just information. But this is going to start providing the information that you would likely see on an interface control document. So that's another artifact in, say, the traditional document-based systems engineering. Instead of doing that all in a document, you could generate that from the information you see here on the IBD. And then you get the benefits that we kind of talked about before, whereas if this item flow changes, then your model is serving as the source of truth, right? So you can update the model, generate the ICD, and anywhere that is referenced, it propagates throughout. So apart from defining the interfaces, we can start looking at the behavioral aspects of the system too. And there's really three types of behavior. So in this one, we're showing a state machine, which is event-based behavior. So we're defining states and modes of the spacecraft, how the spacecraft transitions from one to another state. And then you can also see some of the functionality for each state and mode. So in this one, it's a state machine, so it's all based on states and modes and how you transition, what event is causing the transition. But you're going to have flow-based behavior like we looked at in the activity diagram, or interactions, which we haven't seen yet. So think of sequence diagrams, which is message-based behavior. And you can start linking all this up. So within a certain state, say in this sensing state, this collect observation data, that could be an activity diagram that starts once you enter this state. So you can start linking up the different types of behavior and not just try to think through that from a textual perspective on, what the system needs to do and writing requirements that way. You can flesh it out using the different behavioral diagram types and try to understand the system within one of those use cases or performing a mission. And then that will help you define what the requirements should be. So once you have a lot of that defined, the interfaces, the behavior, even some non-functional things that you can represent as value properties of the block, the spacecraft block, that can all drive now the textual requirements that you can write. And this is what a lot of people think of, these shall statements. The system shall weigh less than a certain amount. And the things that are driving it, you can connect those up using the dependencies to basically say, the textual requirement is refined by other model elements. So if you have a textual requirement that says the system shall weigh less than this, then maybe there's a value property that's linked to it with a refined relationship that's saying this value property is the more concrete version of that textual requirement, or maybe it's a constraint block that gets tied to it. So that's really powerful when you have requirements and then those are linked to other model elements. Again, a stakeholder asks you, why do you have this requirement? You go into the specification, look at the traceability, and it takes you to an activity diagram that says, well, in this context, the system needs to do this. So that's why we have it as a textual requirement. That's great when you can answer that question just on the fly using the model. That's one of the benefits. Whereas if you just had a document with that textual requirement in it, you'd have to think and dig and try to find, where that came from, why it's there. So now we move on to maintain requirements traceability, which is what I was kind of talking about just now, but this is really important. As soon as you start writing requirements, even the high-level mission requirements, you want to stay on top of the traceability, because that is one of the most valuable things about having the model is to query, a system level requirement, what mission requirement is driving it. So you can see here the hierarchy of requirements starts at the high level. Those kind of raw source mission requirements, those got refined. Maybe now they're in shall statement form. Then from there, you have your system level spec, and then keep working your way down. Now you get to subsystem or components. And again, this is where you want to keep in mind the scope and purpose. So if the purpose of this project is just to develop a system level spacecraft specification that you would hand over to someone else and they're going to flesh out the design, then you shouldn't be down here writing requirements for, say, the payload or a certain sensor or some other lower level component, right? Or doing analysis for something down here if it's not going to help the purpose and it doesn't fall within the scope of your modeling effort. So always, again, I can't stress that enough, just keep in mind the purpose and make sure what you're doing is adding value and addressing those stakeholder concerns. So this is a good view of the different types of relationships you can have. So when we're looking at the spec hierarchy, so up here, here's an example of a refined mission requirement. It's part of, basically part of this mission requirement specification. But this would actually be a textual requirement. And you can see the spacecraft level requirement has this derived requirement relationship. So this is just saying that this requirement was derived from this higher level requirement here. And again, once you have this, you can show it on a diagram, or you can just look in the specification of this requirement itself and see these relationships. And it could be, one-to-one, one-to-many. But once you start establishing this traceability, it goes back to those benefits. You can query and see where a lot of these things come from. And even down here with test cases, which we'll talk about later, once you start defining test cases, you can see what requirements that the test case will verify, right? So you can start linking it up that way. Or this satisfy relationship, right? So this is asserting that a model element as part of the design satisfies some requirement. So understanding the different types of dependencies that you can have, and then being able to query that and answer questions, it's very, very powerful. Even some people that don't quite believe in MBSE, they're not sure, they think, oh, this is just, a big show, what's the big deal? If you can kind of show the traceability and how helpful it is in practice, then that's really when the light bulb kind of switches on for a lot of people. I've seen that happen. Where it's like, yeah, you can start at this requirement and then navigate through the model, see where it came from, what model elements are driving it, your test cases that you would use to verify it, all these different aspects just right there in the model. So really, really powerful.
Hey, Thomas, you show
Yes.
here some requirements that are contained within other requirements, say at the very top, and you also have requirements that are derived from others. Could you speak on why you would go one way or the other and what those differences in representation mean?
Yeah, so the derive is really, this is kind of going between levels, right? So if you look at this mission requirements refined, think of that, I think if I go back here, it's like the representation of the specification itself. So if you think of this as a mission, like a refined mission requirement specification, then it's going to have a lot of requirements nested underneath it, which is the containment relationship. So think of that as like one layer of requirements. And then if you go down, now you're at your spacecraft level or system level. And this is just representing that specification, but you can kind of see in the logo, this image here, that in this specification, there's going to be some number of system level requirements. So you can do it like hierarchical like that, where your specification contains all of your spacecraft requirements, and then your mission specification contains all your mission requirements. But that's different than saying, well, now your spacecraft requirement of probability of detection is derived from this mission level requirement, which is detection time. So think of the containment as just a way to organize it in the model. Basically, this is the namespace. This mission level requirement falls underneath the specification. Whereas the derive requirement, we're saying, again, the client side is, for lack of a better word, derived from the supplier side. So it's usually based on some analysis. Like if you know there's got to be some detection time, then that might drive what your probability of detection needs to be, right? So it's two different levels. Does that make sense?
It does. That was super helpful. Thank you.
Okay, awesome. Any other questions here before we push on?
Is that the sensor performance analysis? Does that link to a document?
Sensor.
The link, the hyperlink in it, the rationale. Does that link to a document or more model aspects?
I think that's, like if you had access to the model, I think that's going to link to a parametric diagram.
Okay.
I want to say, I think it's basically another diagram within this model. I might actually show that in the perform analysis. We'll see if that's one of the examples. But yeah, so if there's some analysis that you can do to go from, you know, this level of requirement to now this payload level requirement, you can tie that rationale to it. And again, that's another way you can query it. So if you have the rationale tied to the dependency, it's easy to get to that and say, well, this requirement exists because of this analysis, you know, based on this probability. Again, another huge benefit of having all of this linked up in the model. I mean, you could think of this like you could kind of create a similar view in PowerPoint or Visio or something, but it's not going to be linked up like this. It's all just going to be graphical, right? But now everything is connected in the background, so you can query the model almost any way you could imagine to get this information. So here we move on to the perform analysis. So like we were just talking about, that derived requirement, maybe it's based on some analysis. And here we start defining the analysis context. So if you remember back to the first BDD we showed with the mission context, this is kind of the same idea, where instead of all of the components of the mission itself, now we're looking at the analysis context and defining these constraint blocks that represent different analysis models. So you think of system mass, maybe there's a mass roll-up to figure out the total mass of the spacecraft. Same thing with power, propulsion analysis. There's a constraint block to size the solar array. You could define all of these models as part of the analysis context, and some of these things are going to be interrelated. So once you have the constraint blocks defined with your equation, so let's find a good one. So power margin is equal to the solar power capacity minus the power budget. So equation, and then there's going to be parameters that get fed into that constraint, right? So it's a lot of, it could be cost, power. Just think of like your classic physics-based stuff. You don't want your system or spacecraft to defy the laws of physics, right? You can't have more power than what you have coming in, minus the budget. So you can start checking things like that and linking all of these up together. So not just one model, one analysis model, but also work in the mass. That may play a part in the sizing the array. All of this can impact the other. So you can start accounting for all these things and then do trade studies to figure out what's the best solution, given the stakeholder needs. Maybe we define the measures of effectiveness for the mission level kind of parameters, right? So you can start figuring out what's the optimal solution here, given all these different variables, and playing around with different combinations. So in this case, here's a parametric diagram showing a power analysis. So the parameters that we defined in the previous diagram, they're going to show up here as these little squares on the edge. But what is really cool is, you have the spacecraft defined, you have the block defined, and like I mentioned, you can start creating value properties of the block that represents, say, power or mass, or, down here you have the solar array as a component of the power system, which is part of the spacecraft itself. And it has these value properties: size, mass, cell power density. These are things that you're going to define for the solar array itself. And now you start linking up those values for that component and mapping them to these parameters. So when you start calculating, the solar array sizing, what area, all of these values, these properties of your system is what's driving all of these equations, right? All of these calculations. So if you go in and change your default value for the size, or, any of these really, then it's going to update here. You don't have to go into a different type of model, say this was all separate in some different software. It's all tied together here. So if you update these value properties and the values that are there, it's going to update here. So when you simulate this, you're going to get an updated result. And one thing to note here, simulation toolkit is needed to execute parametric diagrams. So if you have Magic Draw or Cameo, the Sim Toolkit is really fun to play around with. You can simulate activity diagrams. When I was talking about how you can start tying behavior to your state machines, you can do a simulation where when you enter certain states, that behavior will show up, and you can kind of test how your system behaves with certain inputs. Very cool. So in addition to doing stuff like this, where you're calculating values on a parametric diagram, the Sim Toolkit also has some other benefits too. So this one, I did not add a lot here. Just in the interest of time, I see we're running a little over an hour. So synthesize alternative system architectures, that kind of starts bringing all these things together. So if you have requirements and analysis, you can start looking at different configurations of the system. And again, try to figure out, which one makes the most sense, what's the most cost-effective solution. But you can have different alternative system architectures that you could choose from. And depending on the stakeholder needs, kind of pick which one makes the most sense. But if you get a hold of the reference material, there is a lot to this where they go into different subsystems and start doing trade-offs. And it's really interesting, but I didn't include that just in the interest of time. So maybe in the future, if we feel like we could fit it in, I might try to add that content later, but I just wasn't sure if I could squeeze it all in here. But very, very interesting chapter in the book, Architecting Spacecraft with SysML. So the last thing we're going to talk about is integrate and verify system. So again, kind of same idea. We define the verification context using a BDD. And this basically defines all the elements needed to perform a test case, right? So, and we have them stereotyped here. So if you think, the system under test, here's our spacecraft as part of this verification context, and you follow it down. The unit under test, what we're going to test is this scanner, this mid-range IR scanner. So here within the verification context, what we're doing is defining what things do we need to complete this test or this verification of the scanner. So in this case, there's an optical bench that we've stereotyped as test component, just to make that explicit, signal processor, display, and then we're going to have an operator that is running the test, right? So we start defining these things here on a BDD, just like we did with the mission context, just like we did with the analysis context. So same idea, defining these things here, and then we could create an IBD to show, how does the display connect up to the optical bench? How does this connect to these other test components? Start seeing the details there, just like we had our mission context BDD, and then we had an IBD to show how all those different systems connect to each other. We could show that here too. So once we have that defined, you can start defining what the test sequence will be. And you're basically just laying out the order of the verification tests or the test cases. And ideally, each test case, you're going to verify at least one or maybe more requirements. And you're going to define what the pass and fail criteria should be. So in this case, we're showing an activity diagram, and each of these actions are stereotyped as a test case to show that, this isn't just behavior of the system. This is specifically to test, some aspect, in this case, the payload sensor, to make sure it behaves as expected and it meets the requirements. So the test cases are decomposed further. So right now we're just kind of looking at the high level sequence of test cases to verify the payload sensor or some subset of those requirements. But you can represent this at different levels of detail. So you can, like this one, you can see it's got the rig symbol. This is going to decompose, and we're going to lay out basically what actions need to happen to complete that test. And one thing that I noticed, you can represent this at different levels of detail. So early in development, you might lay this out, and like I mentioned earlier, use the SIM toolkit to kind of get an idea if, based on the model you have, if you think the payload sensor will meet the requirements. But that's not necessarily how you're going to verify the payload sensor, right? You can kind of do a predictive analysis and just see, based on the data you have, how it's going to react, if it passes or not. But most likely you're going to have actual components that you're going to test in a lab setup later. If we go back and look at the optical bench signal processor, you're going to actually, test these components. You'd have to have a really trust your model to just run through a simulation here and say, oh yeah, we're good, it passes, right? This is more to lay out how you would do the verification in the real world instead of, writing a documentation or a test plan. Just like you wouldn't create a document with all of your requirements, you start creating the model artifacts and then drive those textual requirements there. Same thing here. You can lay out the behavior needed to verify the payload sensor and then have that drive your actual verification process. And then here is one of those that has been elaborated on. So the verify sensor resolution, which was here. Now you can see the details of that test case, along with what elements in the verification context is responsible for each of these actions. Right, so here's what we're testing, our unit under test, the mid-range IR scanner, which is part of our spacecraft. And then here's what each of these other test components is responsible for. And at the end, we're going to assess whether the component passes or fails. Right, so again, the value of this is seeing it on an activity diagram instead of just a step-by-step process in a document. And then the other test cases, we're just showing the one, but each test case could be elaborated on very similarly. So to summarize kind of what we talked about, we hit the MBSE overview, talked about the 3 pillars, some of the benefits of using MBSE, and then we walked through that simplified MBSE methodology, which is basically a tailored version of OSM. We hit each high-level activity with the exception of the synthesized alternative system architectures, but kind of talk through the benefits of why this is better than using the traditional document-based approach. Keep in mind the process shown, like we talked about earlier, it looks like you just start and go from top to bottom, but this is an iterative process, cumulative, meaning, as you learn more information, you just keep adding that in. So like I talked about down here, once you get into integrate and verify system, maybe that's going to update something in your requirements. Maybe you need to organize the model differently. And then it's recursive, meaning, you're going to start doing this stuff at the system level, look at the system as a black box, but eventually, if it's within the scope and purpose of your modeling effort, you're going to dive down and kind of do the same thing for subsystems too, start exploring those requirements of your different subsystems and even down to the component level. Again, if that's part of the scope for your effort. So this is really key here, iterative, cumulative, and recursive. Keep that in mind. It's not as simple as just starting here and walking through the process and saying you're done. You have to circle back quite a bit. So, any questions?
One big comment that I had is that we've been organizing some of our model materials for integration, and we've been understanding what kind of tests that we need to do. It's specifically verification by test, but I'm now seeing for those that are on who are working on that model that we should probably be defining those test blocks as test cases. I've seen kind of a critique of SysML that these are defined as test cases and not verification cases, because you would think that you'd want to do analysis or inspection or demonstration. So a lot of people I've heard using test case are actually using it as verification case. But it's not so much a question, but something that I've learned from watching the seminar that we can implement in our own model.
Yeah, I see what you're saying, because you're right. Verification, it's, there's 4 different types, and we're just assuming or we're naming it test case, or at least that's what Friedenthal did here. And that's the way I've always heard it referred to in the context of like a model or MBSE. But I mean, you make a good point. Maybe it's not necessarily a test. Maybe it's more of a demonstration, right? Where you're not measuring something, you're just observing that it can do it. So it's a good point.
Might reach out to OMG, either call it verification case or give us analysis, inspection, or demonstration cases as well.
Yeah.
Might be helpful. Ben, Noah, do y'all have any specific questions? I certainly got a good overview here. And I do think it's important to point out that I have seen many people describe the pillars of MBSE, and the ones that I usually use come from Jerry Sellers and Bruce Chesley, actually. Jerry Sellers invented the FireSat concept, I believe. But one thing that Dr. Thomas tends to stress is that there's no one right way to do this. And then I certainly think that the three pillars you've described are relevant here as a way to conceptualize this.
Yeah, awesome. See, I had thought about that too, because I watched your video and I noticed that I think it was 4 pillars that you referenced.
Yeah, Bruce Chesley and Jerry Sellers, they say, it's the architecture framework. What are all the products that you need to define inside your system? What is the process framework? What are all of the ways that you can mature these products? And then you have your modeling language, which is more specific to what you were talking about here. And then finally, you have your ontology. But model-based systems engineering is a tool in the tool belt. So you do have to decide what in your architecture and process frameworks are you going to apply the modeling language and modeling tools to. Because as you mentioned, we don't model for the sake of modeling. So that's probably something that needs to be said in the introduction to MBSE seminar.
Yes, I agree with that. And I've actually seen people bring up that point when we talk. I guess the 3 pillars of MBSE that we talk about are kind of simplified. And I think the 4 pillars that you mentioned get into a little bit more detail. Like at the bare bones, you need a tool. You need to understand the language and then some process or methodology to follow. But the framework is key too. And a lot of people argue that even if you don't think you are using a framework, you are. You just don't realize it, right?
Yeah, we try and tell everybody that everyone's a systems engineer, whether you know it or not. It's just how well do you understand the application of what you're doing. I think it might be smart if Thomas, you and I could figure out a way to contextualize the 3 pillars that you've mentioned here within the modeling language part of the 4 that may be just a little bit more broad and maybe don't include some aspects of what we would put in the model.
Yeah, that I'm definitely up for that, man. We need to stay in contact and talk about that. I like that idea.
Yeah, let's figure out the best way to do it and shoot it over to Sandy.
Yeah, there we go.
So sorry, I asked Ben and Noah if they had any questions and then proceeded to talk for 5 minutes.
Are you able to go to, I think it's either the next slide or the slide after? Yeah, here, or yeah, before I say anything, I just want to look at this, make sure I read something right. Okay, never mind. I think I read something wrong, but all right.
Okay. Yeah, keep in mind, I put a link in here if you guys want to go download this model and kind of poke through it and see what else is there. There's a ton of diagrams throughout the book, and the model is pretty good to look through if you're interested. So definitely check that out if you'd like.
Yeah, that would definitely be nice to just kind of walk through a bit.
Mm-hmm.
JP has said, I'm presently taking a class on Comet UML for software development. You see many parallels between UML and SysQL and object-oriented systems engineering method. Do you have any learning resources you recommend for implementing this process in a more generic context? Thomas, I'd love to hear your response, but I'll go ahead and say that SysML Distilled by Lenny Delligatti is a phenomenal first introduction to SysML and the various ways that it can be used. There is, in more general context, this is you've got a big book, I don't know if you can see here, a practical guide to SysML, which is by Sandy Friedenthal, Alan Moore, and Rick Steiner. That's pretty helpful. And the thing that I try to convey is that it's hard to do this stuff without actually practicing. You can read these books and learn as much about the 9 diagram types in SysML as you can, but until you get your hands into it and you start understanding what you can do in the context of your system, it's hard to blanket say it's going to be the same for everyone, because it probably won't be.
Yeah, I agree with you, Michael. That was a big thing. Well, yeah, I agree, because a lot of people, they learn SysML, they get the certifications and they know the language, and then they get to the tool and they're like, well, okay, now this is different. How do we use the tool? So then there's like a learning curve there too. And then some people just completely ignore the methodology aspect. They're like, hey, we got to go do MBSE. Let's start just making diagrams, right? So the 3 pillars are definitely important, or at least the ones that I talked about today. But as far as a more general context, yeah, SysML is distilled is good for the language part that I can remember. But a practical guide to SysML, there's some examples in there. I think it's a residential security system.
Yeah, it's chapter 17.
Yes. That's really good. It's kind of simple, easy to understand, and they walk through the OSM process top to bottom, kind of like we did here. Instead of a spacecraft, it's a security system for a house. So you'll get kind of the same diagrams, different, same views, but a different type of system that might help in a more general context.
Yeah, I'm looking at it now. You're absolutely right. I think an important point here is that it's not just spacecraft. You can do this for anything. And I think Thomas and I would argue that we should be using this more in a large variety of systems, not just space systems.
Yes, absolutely. And I had to keep that in mind when I was writing, kind of building this presentation, to try to think more about the spacecraft, because when we help people, we do consulting and training. There's automotive, people in the automotive industry, airplanes, unmanned aircraft. I mean, even think of like washers and dryers, right? Like stuff like that. That people are using MBSE to do the systems engineering more effectively. Like any kind of system you can think of, MBSE can be beneficial for. So I kept, I kind of take that mindset, and I'm used to different domains, and this is going to add value no matter what. But I had to kind of stay focused in. It's like, well, this is geared more towards spacecraft. So I hope I did a decent job, at least trying to stay on target there. The example, the reference material helped me, but you're right. I mean, not just spacecraft, it's really any system that this could be beneficial.
JP, you might have seen different aspects shown, the mission context. That can be said a variety of ways. If it's not a mission, you might be able to show a system context is kind of different than the mission context, but you might be able to say a project context, and the system might exist within that project. So this, you can see you have the mission context in that enterprise, or what your, say, business or consulting firm, whatever, what context do they exist within? You can show this, and it's not just specific to spacecraft missions. So looking at a couple of these diagrams and then trying to apply them to what you're working on, I think would be incredibly beneficial, especially if you can get your hands on a SysML program that Thomas was talking about early in this presentation. Noah, I saw you unmuted. Did you have anything?
Sorry, I was double muted. No, I mean, I'm fairly new to the world of systems engineering in general, so I'm really just still trying to absorb. I don't really have any specific questions.
Yeah. Well, hopefully this presentation will be useful to a lot of people in that same boat. And Thomas, do you have any closing wisdom for us?
Just stick with it. I know if you're first learning this, I remember when I was first learning it, it's kind of overwhelming, you know, learning the language, the tool, and, you know, how does it all come together? And it's kind of overwhelming for some people. There's a lot to learn. It's kind of a steep learning curve, but man, stick with it. It eventually all starts coming together. And I liked it from the very beginning. Like I took classes at UAH on this and learned a lot, and then doing it in practice, like you said, like you can learn a lot watching videos and just studying, but the more you do it, the more you practice, the better you'll get, and the more things will start making sense. So I say just stick with it. Don't give up.
I think like Thomas said early on, we are shifting from document-based to model-based kind of ubiquitously. It doesn't matter the sector. This is not going away. We're just going to get better at it and get more effective at representing systems in a concise way that can be communicated to both external and internal stakeholders.
Well, I am all for models I am all for models instead of documentation.
Yeah. The purpose of systems engineering is not to produce documents, it's to make decisions. And that's what we do here. So Thomas, thank you very much. We thoroughly appreciate your time and your expertise. Just thank you. And we hope to see another presentation if you have it in you again on maybe specifically one on that analysis of alternatives, something like that.
Yeah, absolutely. I appreciate you having me. This was great. So yeah, we'll stay in touch. Maybe we come up with another topic because I've enjoyed it.
Yeah, this is fun. Thank you to everyone who attended, and we appreciate your time. Bye.
Thank you.
Thank you.
All right, thanks, guys.